All right. So as usual, let's talk about some announcements. Homework 7 is due tonight on Gradescope, Friday, October 30th. Homework 8 will be posted later today, and it will be due after a week. Studio 5 has been extended because many students had issues completing all the 3 tasks. And since next week is exam week, I think I should not be expecting you to work on a completely new studio for next Wednesday. So I just extended Studio 5 for another week. So now it's due November 4th, next Wednesday. For those of you who have already completed Studio 5, you can use that time to prepare for the exam, review the lectures online and the videos that I posted as outside of class review. You can watch that. So spend your time on that. Quiz 16 is available on Gradescope for you to answer. And exam 2 is coming up next week, so next Friday. And the logistics are going to be very similar to what we did for exam 1. Questions or concerns about this? Going once, twice. We get the same 2.5 hours for submission. Yes, that's right. Same 2.5 hours of submission. You can take the exam at any time you want. Just start it before 9:30 so that you get the full 2.5 hours. No, it'll not be cumulative. It'll be focusing mainly on topics that we learned between exam 1 and exam 2. So I will be posting exam 2 topics and back exams and all that to the Piazza page very soon. Oh yeah, I will be posting practice exams, Ian. Today's lecture material, yes, it's going to be on the exam. All right, so I think that's it. Now let's talk about something that it's new, and the reason why it's new is because we have not yet looked at how to store information in our logic circuits. So latches is one basic element to store one bit of information. So that's a latch. Basic element to store one bit of information. And I suppose when you hear the term latch, you can imagine the latch on a door, which is used to open or close the door, right? So that's what it means. I can store one bit of information, and whenever the user chooses to change that bit, it could be a 0, could be a 1. So you can change that bit and then keep it stored for as long as you want. So that's what we are going to talk about. How do you implement latches? And we will start with this. What have we covered so far? We were in the combinational. No, it's not like a transistor. It's still using logic gates. However, we need to connect the logic gates in a certain configuration to get the storage ability. We'll talk about that. We have covered number systems, computer codes, digital circuits, Boolean algebra. We also looked at combinational circuits. Now we are moving on to a new topic, which is sequential logic circuits. So the main difference between what you saw until now in the course and what is coming up from now onwards is going to be the fact that combinational circuits had outputs that depended on the combination of the current inputs. So when you change the inputs, the outputs changed immediately. There was some delay, but they changed immediately because of the change in the input. Maybe I need to use this. So the outputs depend on current inputs only. That is for the case of combinational. Now, for the case of the sequential circuits, the outputs depend on the current inputs, which is the same as combinational, and they also depend on the sequence of previous inputs. So sequence of previous inputs. Hence the term sequential. So that's one key difference between combinational and sequential. And of course, if I have to depend on the previous inputs, I need the ability to store bits of information, and the way storage or storing ability is implemented is by using feedback connections. And we'll talk more about that. So that's one key difference. So a general block diagram of a sequential network or a sequential circuit comprises of certain inputs and certain outputs. Those are all the way to the left and right, respectively. You may have a combinational network which does not have any memory in it that you are controlling with the inputs. And after the combinational part, you may have these storage elements. They can be of different forms. So for example, we can start off with the concept of latch, which is the basic element, and then we can make flip-flops using latches, and then we can use flip-flops to make registers, and then we can also use flip-flops to make counters. So all those components would fall under the category of storage elements because they have some sort of feedback that is present which allows things to store bits of information, either one bit or multiple bits. Now, coming back to the combinational network doesn't have any memory, right? So this is going to be muxes, decoders, and so on. Those do not have any feedback. So when the inputs changes, the outputs change as well, right? So the straight path that you see over here, that corresponds to just the combinational behavior, no memory. But then some of the outputs from the combinational network, you might be interested in storing them. So some of the outputs that you are interested in storing go into the storage elements, and we have talked about what they might be. And then there is a feedback back into the combinational network over here that allows that to be stored. So this is your feedback path. At this point, it might be a little bit difficult to see how things are going to play with each other, but as we move on and look at these components in detail, you will see this block diagram will make more sense. Now, there is something called the next state, which is the output of the combinational network when the inputs changes. And then once you store it, there is a current state, right? So there is a current state and then there is a next state. These are essentially outputs before and after a particular event happens in the network. Again, we'll talk more about that here. So let's start talking about how we store information, and we'll build it up with a simple discussion on a buffer. Now, what you see over here is a buffer. Input is Y, output is also Y, and the propagation delay through the buffer is represented as T sub PD. If I have this buffer with the propagation delay of T sub PD, if I give it a 1, I have a 1 here. If I give it a 0, I have a 0 here, right? So that's my one basic component in the buffer, which I'm going to use along with feedback to store memory. So actually, we talked about this a little bit earlier. So delay here is actually going to help us store information. So it's sort of counterintuitive because you might think that propagation delay is a problem in the circuit and you would want to minimize it as much as possible. But having the delay actually helps us store information, and we'll see that in a lot of detail later on in the lecture today. So that's a simple buffer. Output equals input after the propagation delay of the buffer. Now think about how you would use this buffer in order to store the bit of information. And I can do that by simply connecting it in a feedback network. So for example, if I took, let's see, blue, sure. If I took this output and I connected it back to the input over here, what would happen? Say for example, if I make the input 1, my output will become 1 after some propagation delay, but that output is being fed back to the input, right? So unless I change the input here, that 1 will keep going round and round, right? Would we worry about shorting? Well, in this case, it is just a logic high being fed back to the input, right? Just a connection of the output to the input. So when I change the input to 1, you see, if I make this guy 1 here, the 1 goes through the network and is coming back to the input. So 1 is connected to 1 here. So there's no short of the circuit. How would we access variable y variable, right? So you would need to bring this out here. Let me use black, and then use some 1 or a 0 selector here, maybe a switch, right? Connect that to a switch, and then that goes into the buffer and comes back over here, right? So even though I remove this, I remove this switch after I make it 1, that 1 will keep going back in circles in the buffer, right? So the fact that it is memory, I'm going to remove that, right? So even though my switch is removed from the circuit, that 1 will continue to be there. And this process is going to keep repeating. But when you switch the buffer being 1 to the setting input low, that would mean, right? So when I make this a switch of 0, this is just for the sake of discussion, guys. You would not implement memory by doing this. Here I'm just laying out the fact that with a feedback network, we can have the ability to store. This is not a practical approach. This is just to lay out the theory for this. So all your concerns are valid, and they will be addressed in the actual latches. All right. So taking the output of the buffer and feeding it back to the input, that's one way of doing it. But buffers, as we know, are actually 2 back-to-back inverters. So if this is propagation delay, then half of the propagation delay corresponds to one inverter and half of the propagation delay corresponds to the other inverter. Now, if I somehow figured out a way to make this a 1, then that would mean that this guy would be a 0, this guy would be a 1, and then comes back. So that would be a stable state. And the other stable state that is possible is, if I figured out a way to make this a 0, this will be a 1, and that will be a 0 again, and that is also going to be stable. Meaning there is not going to be any confusion. Things are randomly not going to change between 1 and 0 at any stage in this back-to-back NOT gate configuration. So buffer being implemented as a pair of inverters. But as you guys pointed out, that this is not going to work very well because I don't have the ability to control the input in a very efficient manner. So what we'll do is we'll look at a configuration called cross-coupled NOT gates. So what we have over here is 2 cross-coupled NOT gates. And it's called a bistable element because it has 2 stable output, 2 stable conditions in which the circuit is not going to fluctuate between a 0 or a 1. It's not going to go 0, 1, 0, 1, 0, 1. It's going to be stable at those points, and there are two of them. So let's talk about that. This is the simplest sequential circuit that you can think of. Two NOT gates connect the output of one connected to the input of the other, the output of the second one connected back to the input of the first one. Now let's say we have made this guy. So let's see if I can somehow make this a 1, right? If I make that a 1, V in 1, if I make that a 1, V out 1 is going to become a 0. So Q is the letter that is used to indicate the output of storage elements. And there is also the active low version of Q, Q sub L, that is also available from this bistable element. So going back to this, if I make the input 1, the output becomes a 0, and that output actually comes back over here. So that output 0 is being fed here. The output V out 2 will then become 1. And because this is 1 and this is also 1, right? This configuration is going to be stable until you actually change V in 1 or V in 2 by using a switch or an external input. That is going to be stable. So that's one stable condition when Q equals 0, right? That's one. The other input situation that could be stable is, consider the input here as 0. If that input is 0, this guy will be 1, that one will come down here, that one will keep this at 0, and that 0 goes back again over here, right? So that is going to be your second stable point when Q is 1. The other thing I want you guys to note is Q, when it was 0, Q underscore L was 1. When Q was 1, Q underscore L was 0, right? So in both those cases pointed out in red and blue, Q and active low Q were exactly the opposite of each other. So I can write this as true form of output and this is going to be the complemented form of output. So by connecting two NOT gates in a cross-coupled configuration, I can store one bit of information. I can provide that bit of information through V in 1 or V in 2, but my Q and QL will be stored as long as I keep power active for both the NOT gates. Now, I hope while we were discussing this, you guys still had that concern about how to effectively change the inputs here, right? So there was still that point that left as a question mark. I still don't have a very good way of controlling this bistable element. So we need something that has more than one input, which is why we go to NOT gate. Let me go on first, and we will go on to NOR gate configuration, where we will have an ability to change the input and store it properly. So that's coming up later. Let's go back here and let's talk about store one bit of information. Now, when you think about storing one bit of information, there are maybe a few things that you would want to do, right? So for example, if I'm asked to store one bit of information, then I would want to do this. 1, make output 0 and store it. The other thing that I would want to do is make output 1 and store it. I suppose those are the only two things, right? If I'm interested in storing one bit of information, then I first need the ability to choose what bit it is, 0 or 1, and then once I decide which one it is going to be, then I need the ability to store it. So this, making the output 0, we are going to refer to that as reset the latch, make it 0. And we are going to refer to make the output 1 as set the latch. And the last combination here, to store it, we are going to say hold or store or memory. So those are terms that are often used to indicate that right now your latch is in the hold state, or it is storing things right now. So you may want to reset the latch and store it. You may want to set the latch and store it. That's it. Those are the only two things that that come to mind, right? Those are very obvious. There can be other things as well, and we will see what some of the common latches and flip-flops, but this is the basic functionality. That's what you would ideally want. Now let's go back to the cross-coupled NOT gate configuration and take a look at why there are two stable states and what would happen if there was some noise at one of the inputs. Let's take a look at that. So this is a graph of the characteristic of a CMOS NOT gate, right? So for a CMOS NOT gate, let's see, you have something like this. Then if your input is very high, input is sketched on the x-axis. If input is very high, then the output is low. And if the input is low, the output is high, right? So this is the transfer characteristic of a CMOS NOT gate that we looked at earlier in the course when we were talking about noise margins and those kind of things. So let's try to apply this to our cross-coupled NOT gate discussion. So what I'm going to do is I'm going to erase this here, and in red maybe I can draw two NOT gates and I can put them in a cross-coupled configuration. So simply what I would do is I would bring the output here over there and then go here and then go there. So that's my cross-coupled NOT gates. I'm calling the output over here Q, and I'm calling the output over here Q sub L. The same bistable element that we just talked about. Now, let us suppose that our input right now is at 2.5, right? Suppose this is at 2.5 right now. When your input is at 2.5 volts, what would be the output? Well, this guy says, if you are at 2.5 right here, then your output is also 2.5 over here, right? Because we are right now operating right in the middle. So if you see this, 2.5 here makes it 2.5 there, and that 2.5 is available here, and that will keep this at 2.5, right? So all the places are at 2.5. But that point is very, very difficult to maintain in practice. Because what could easily happen is a little bit of noise due to thermal noise or maybe some instrumentation noise. Some little noise might affect one of the input voltages. So what we'll do is this. We'll try to change this input voltage right from the center to maybe a little bit up or maybe a little bit down. So let's see what happens because of that. I'm going to first erase these off here, and I'm going to start with 2.3. Suppose due to some noise, very small amount of noise, the input of the top NOT gate became 2.3. Instead of 2.5, it became 2.3. Now, because of that, it will cause many changes in this cross-coupled network, and let's go through them. So when the input over here at the top changes to 2.3, what would happen to Q? Earlier it was 2.5. What would happen to Q now? Let us look at it from the transfer characteristic, right? So it would become high, right? So let's talk about voltages here. So if you go 2.3, so you're going left, right? As soon as you go left here, what happens to the output? It becomes high, and let us say that voltage is somewhere close to 4 volts, right? Somewhere close to 4. And that 4 volts, I should probably say 4 volts. That 4 volts is available over here. When the input to the second NOT gate is 4 volts, what happens to the output there? You see this? When the input is 4 volts, the output is very, very low, right? So it'll go down. So maybe I can write that as say 0.2 volts. So these numbers are not exact, but just to give you a sense of what is going to happen. The moment this guy goes to 0.2, that is actually being fed into the NOT gate there, right? So in blue, I can write the next 0.2 is available here. So the moment that goes to 0.2, what happens to the Q? So you're somewhere here now. So the output over here jumps to 5, right? That 5 comes down here, and that will keep this at 0. And that will become 0 here. You see what happened here? The moment it went slightly away from the center, it ran up over here, right? There was a avalanche of changes, and suddenly we ran up this, and then we ended up over there. Now, in the same way, if we started with 2.5 and made it 2.6 and 2.7, what would happen? We would roll down here, right? The opposite, exactly. We would roll down to the other end of the graph. This phenomena is what is called as the bistable element. You see, it became stable only when it reached at the end here. It became stable only when it reached at the end over here. It was not stable anywhere in the middle. You guys see that? So this phenomena can also be, that's what is being described over here. And that phenomena is called metastability. So when we were right at the top, meaning at 2.5, 2.5, right in the center of the graph, we were very dangerously stable. That's metastable, because the moment this ball kind of was pushed on one way or the other, it quickly rolled down to one of the two stable states. And one of the two stable states, what were the two stable states? The states where output is 0 or output is 1, right? So those are your two stable states, but right in the middle, it was stable, but only momentarily, right? Because a little bit of a change, which is very often in practice, would cause an avalanche of changes. So those changes are being described over here by considering the input on x-axis, which is the same as the output of the second gate. The output of the first gate is the same as the input of the second gate. So when you start here, you go and become stable there. The center point is called metastable point. And when you start going down, you go and become stable all the way to the left, to the right. So two stable points and one metastable point in this particular configuration of two cross-coupled NOT gates. Questions about this? So all we are doing is we are taking a look at how a small change at one of the inputs to the NOT gate causes the bistable element to make many changes, but it will eventually become stable. So the stable point over here, let me just highlight that in yellow here. It will become stable over here. And after that, there's nothing else to change. It will be stable there. All right. So we talked about the hill here, ball rolling down. Sure. So metastability is a phenomena that we often see in sequential circuits, and there are going to be a few parameters of flip-flops that we are going to have to worry about to avoid being in the metastable state. So you always want to be in the stable states. You do not want to be in the metastable state. So in order for us to avoid metastability, circuits will have to obey setup and hold times. So when we get to talking about flip-flops and a clock input and some data inputs, we'll discuss setup and hold times, which we will have to obey in order to avoid metastability. All right, let's take a look at another bistable element, but now we are going to try to control it, because as we pointed out earlier, there was no good way of controlling the input to the two cross-coupled NOT gates. So let us try to answer that. How do you control it? Well, add control inputs, right? So if you want to add control inputs, that's the answer. How do you add control inputs? Well, you would have to have a logic gate that has more than one input, because one of the inputs is being used as the feedback input. So that's where our two cross-coupled NOR gates come into the picture. So this guy is the famous latch, set, reset latch. S stands for set, R stands for reset, and latch stands for storing one bit of information. How does this relate to what I want to do? I want to either set it or reset it, and I would want to store it. Set, reset, latch. We'll spend quite a bit of time trying to analyze this. Let's see. This is called a two cross-coupled NOR gate configuration. Two cross-coupled NOR gates. And the inputs appropriately have been chosen as S and R. S standing for set, R standing for reset. We still have the outputs in true form and complemented form. So let's try to write that as well. Q in true form and Qn in complemented form. And we are using NOR gates to do this. On the right, there is a table. What should I call this table? Latch table, truth table. Okay, so truth table was the table for all combinational networks. But for latches, this table is going to be called characteristic table or the next state table. So this is the characteristic table of SR latch. Now, before I actually walk you through the table itself, what I want to do is analyze it. Analyze this particular configuration. Now, to do this analysis, I would consider the NOR version. There is also a NAND version. So you could replace these NOR gates with NAND gates. You would have to switch the inputs R to S, S to R, and you would still be able to implement the set reset latch that way. But what we are going to do here is use the NOR version of the SR latch to do the analysis. Now this is going to be quite critical for your understanding of latches, which are the fundamental element for almost everything that you will see later in the course. the first thing that we would want to agree upon is the truth table of the NOR gate. The truth table of the NOR gate is written in front of you here, and one conclusion can be drawn by looking at the truth table. The conclusion is, if one of the inputs is if one of the inputs is 1, right? If one of the inputs to the NOR gate is 1, the output will be a 0. You see that? And that statement is written over here. If any input is high, then the output is low irrespective of the other input. I don't need to know the other input. If one of the inputs is high, immediately I can say the output of the NOR gate is going to be low. This is going to be the rule of the NOR gate that we are going to use to analyze the configuration. We'll use this rule many times. So I hope you guys agree with this particular statement. This is an important property of the NOR truth table. Any input is high, right? The output is low. If the input was low, then I would have to wait for the other input to come in, right? If one of the inputs is low, then I cannot make any conclusions. I have to wait for the other input. I need to know the other input. But if one of the inputs is high, I don't need to wait for the other input. I can just tell you that the output is going to be low. Using that, let us try to consider the two cross-coupled NOR gates, and we'll do this case by case. Here is case 1. In case 1, we are we are making the S input as 0 and the R input as 1. So let us see what happens if you have S as 0 here and R as 1 over here. So you guys have to help me out a little bit. Can I say anything about Q right now? Q is 1 right away. So I didn't have to wait for finding out the other input of the NOR gate. Q is 0, right? I didn't have to wait for this guy, right? As soon as I said this is 1, after the propagation delay of the NOR gate, Q is going to become a 0. That's because of the property of the NOR gate that we just talked about. Any one of the inputs is 1, output is low. That 0, where is it going to be? That 0 is going to travel down here and is going to be available over there, right? Now this input is 0, that input is 0. What about Qn? Qn is going to be 1. Absolutely right. Now, is this going to be stable? Absolutely yes, because you see that 1 is going to be available over here. 1 and 1 will keep this at 0. 0 and 0 will keep this at 1. This is going to be a stable point of this circuit. This is a stable state here, right? 1 is going to be available there. 1 nor 1 will keep this at 0. 0 nor 0 will keep this at 1, right? I hope you see that. Now let's try to do something. Let us try to store the output, because we have already made it 0, right? We have already reset the latch. You see this? Our input became 1. We wanted to reset the latch, and we did. Q is 0. Now let's try to store Q equals 0. So we are trying to store one bit of information, and that bit is 0. In order to store information, you have to make S as 0 and R as 0. Both inputs need to be 0 in order for you to store it. And we'll prove this. So what I'll do is I will change the input here. I will make 1 to 0, and this is 0. I will keep this at 0. So as soon as I change 1 to 0, the question is, there was a 1 there, right? So there was a 1 there from earlier. Did that 1 change because of this change to 0? You see, this is going to be a critical question here. As soon as I change the inputs to 0, immediately, is this 1 going to change? Or it will change maybe later? The answer is no. Yes, the reason is this. Later, yes, maybe. So the moment I change R to 0, that change in the input will need some time to be reflected in Qn. But from earlier, Qn was already 1. So if I change the input on this line is still going to be 1 initially. You guys see that? That is crucial to note here. And because that is going to be 1 there for some amount of time, tell me what Q is going to be. 1. No. 0, right? Because any input to the NOR gate is 1, the output will be 0, right? So 0 will continue to be 0. That 0 in blue will travel down here. So let me move this a little bit to the left and right in blue. That 0 changes to 0 now. So no change. 0 nor 0 will keep this at 1. You guys see it? So the whole analysis depended on this guy staying at 1 for a very short duration of time. So guess what helped us? Propagation delay of the NOR gates helped us store the information. How am I able to claim that the bit is stored? 0 continued to be 0. Even though I changed the input, output did not change, right? This is my Q, and this is my last Q. Similarly, this is my last Qn, and this is my Qn. Storing more than 1 bit is probably a headache. Well, in order to store more than 1 bit, you just use multiple latches. So the same thing applies, but you're going to use multiple latches to do it. With one latch, you store 1 bit of information, and also its complement. So this particular state, which is Q equals 0 and Qn equals 1, is called the reset state. Reset state of the set reset latch. I think if S stays at 0, the Q will not change. Well, for storing, I have to have both inputs go to 0. And for setting and resetting, I can play with the S and the R inputs. We'll do case 2 and case 3 as well. So when we try to store the bit of information by making S is 0, R is 0, I hope you guys saw that Q was the same as last Q. New output was the same as the previous output. And Qn was the same as last Qn, indicating that we were able to store the bit of information. So this is called the store state. So right away, if your R is 1 and S is 0, you are in the reset state. And when you make both inputs 0, you are in the store state. Let's talk about the other case, case 2. Now you have S as 1 and R as 0. This is going to be, of course, called the set state because you have made S as 1. So let's do that. Let's use red to indicate the start, and then we can store it. 1 here, 0 here. That's our starting point. Who can tell me, do I know anything about the outputs here? Qn or Q maybe? Qn is 0. Perfect. I don't have to wait for the other thing. Qn is 0 right away. That 0 goes up here. 0 not 0 will keep this at 1. Now the question is, when did this become 0? So let's suppose TPD and TPD. I'm saying that the propagation delay of the NOR gates are TPD. So this became 0 after TPD. That's good. This became 0 after TPD. When did this become a 1? 2PD, 2 TPD. Yes, absolutely right. You got it. So for this guy, I was able to find that out very easily because of this one. But for this guy, I had to wait. First for here, then for here. So 2 times the propagation delay. You got it. All right, let's change it, right? Let's try to store it. We have already set the latch. Q became 1. Let's store it. So for let's storing it, I can actually copy this and paste it over here. Let's try to store Q equals 1 by making both S and R as 0. Let me do that in blue. I'm going to change this to 0. I'm going to change this to 0 as well. So when I change S from 1 to 0, or when I change R from 0 to 0, do you think any of the outputs will change now? So when I change 0 to 0, right? Did this 0 change at that same time? No. That is going to stay as is because there is a propagation delay that is involved. So when I change this guy from 0 to 0, that stayed at 0. 0 nor 0 will keep this at 1. That 1 will come down over here. 1 nor 0 will keep this at 0. You guys see it? We were again able to store the output. Even though we changed the input, in this case we changed S from 1 to 0, the output did not change because what saved us was the propagation delay of the NOR gates. So this applies again. Q is the same as last Q and Qn is the same as last Qn, as you can see. Actually, I can maybe copy these things. There it is. So again, we have the set state. Okay, let me write that as well. What is set state? Set state is Q equals 1, Qn equals 0. That is called set state. So we have actually discussed the reset state of the latch, set state of the latch, and the store state of the latch. Let's see. Let's go on to a confusing case. let's see. So we can only store information for a certain period of time equal to the propagation delay. No. So as long as you have S and R to be 0, 0, the bit of information will be the same. It will not change. As long as you have S and so the storing of information is controlled by the S and the R inputs. So if you want to store for as long as you want, keep S at 0, keep R at 0. Let's go on to the slightly different and confusing state here, which is R is 1, S is 1. So when R is 1 and S is 1, actually let me remove this here. R is 1, S is 1. So let's do this. Start with red, make this one, make this one. If I do that, what is Q and Qn? Both are 0. That's your first problem. Why is it the problem? Because I claimed earlier that Q and Qn should be complementary in nature. One is active high, one is active low. But right now, both are giving me the same value, 0 and 0. Is it stable right now? Yeah, probably it is stable right now, but soon it is going to be unstable. You will see that very soon. It will be unstable. So this is going to be called a metastable state, and you will see why. This is 1, this is 1, outputs are 0, and now let us try to store it. So now let us try to store the outputs Q. Let's try to store Q equals 0. What do I need to do in order to store? Well, I need to make S as 0 and R as 0, right? If I make S as 0 and R as 0, you see this, what I'm doing? I'm changing this to 0. At the same time, I'm changing that to 0. So what is going to happen? Right now in your head, if there are things that are going, is it 0, is it 1, is it 0, is it 1, then you are analyzing it correctly. So let's do this. What I'm going to do is constantly changing, absolutely right. So I will begin this analysis by assuming that I did not know this guy. I just knew the first guy. Qn is 0. I did not know what Q is. Let us suppose that is the case. So let me, instead of erasing it, maybe I can write it in gray perhaps. So essentially what I'm saying is I'm ignoring Q is 0, but I know it is 0. I'm just not analyzing it using that. That is still 0, right? So that 0 over here is available over there. What is going to happen to Q in this case? Should be a 1. So this guy immediately changes to a 1 there. That 1 comes down here. What happens to this guy now? Oh, hold up. That was 0, right? So this was 0 and that was available here, right? So this 0 was there and that made it 1. That 0 was here and that made this guy 1 as well. And if you keep doing this, because you changed R and S down to 0, 0 at the same time, you will see that this will go 0, 1, 0, 1, 0, 1. And this will go 0, 1, 0, 1. It'll constantly keep changing. This is called metastable state. It was only stable as long as you put R is 1 and S is 1. But the moment you try to store it by making both inputs R and S down to 0, 0, we had a problem. Any delay between input changes would stop this. Yes, you're right. If we have these changes at different times, we may not have metastability. But if the changes happen at the same time, that's when the problem occurs. But even before that, we had a problem, right? Q and Qn were the same. They were not opposites of each other. They were not complementary in nature. So the one problem here is, let me write this. What happened? Q became this. 0, 1, 0, 1, and so on. Qn became 0, 1, 0, 1, and so on. They are changing constantly. So this is a not allowed state. So when you have inputs that are exactly the same, 1 and 1, there are two problems. One is both the outputs are exactly the same, 0 and 0. The other bigger problem is you cannot store that particular state because that will cause the inputs to go crazy, 0, 1, 0, 1, 0, 1, constantly changing. So what is a possible solution here? Possible solution is never allow inputs to be the same. For example, if I add a NOT gate here and I only control R input, then I will never have the situation of 1, 1. What about reset state or store state? Store, yes. So if I do that, like Preston pointed out, the problem is that we will need something else. To store. Because the moment we have this, we have lost the ability of making R and S inputs both as 0, 0. So we lose the store state here. So we would need some other way to store the bit of information. So there is a solution, but we would need something else to for us to get the store ability back. So this is done in the D latch, which is coming up later. So right now, what do we have? We have 4 states. Actually, this is called Q equals Qn equals 0. And it is the not allowed state. Couldn't you add a buffer to R and S to add Oh, if you add a buffer, then the previous 2 states get affected as well, right? Which are more important to me. The reset state, set state, store state, all get affected because of that. Because the whole idea is relying upon propagation delay. So I cannot change any path's propagation delay. All right, let me go back here to this slide and talk about the characteristic table now. The first case that we discussed, case 1, was reset state. Where is that? Right here. We had to make S as 0, we had to make R as 1, and at that time our Q was 0 and our Qn was 1. That was case 1. And we called it reset state. And it will be in the reset state as long as you keep S at 0 and R as 0. The second case that we talked about was the set state. So for set state, we had S as 1 and R as 0, and at that time output Q became 1, output Qn became 0. So that was our set state. And from each of those cases, from each of those states, set and reset, we tried to store the information. And to store the information, we made S is 0 and R as 0. And the moment we did that, our Q was the same as last Q, and our Qn was the same as last Qn. So that was what that was our memory state, or hold state, or store state, whatever you want to call it. And the last state here is the not allowed state. When you made S as 1 and R as 1, Q and Qn both showed up to be 0, but the problem was that we were not able to store it because of metastability occurring. So that is our not allowed state. Now, I want to take a minute here to talk about some terminology. We used Q and last Q, right? Let me talk about some variations that you might see. I will add a page. Well, I can just show you here. So Q and last Q. Sometimes you will see in textbooks or other literature, those two things being referred to as different by different nomenclature. So for example, last Q may be referred to as Q previous, Q subscript previous, and Q new here. So that's another possibility. And some other times you might see Q here and Q plus over here. But the differentiation should be this. There are two states, current state and the next state, right? Last Q and Q. So that means what it was and what it is going to become. Q previous, Q new, what it was and what it is going to become. And they're all talking about the same Q, by the way. It's just the Q, not Qn. They're just talking about the same output right here. So you could see last Q and Q, or you could see Q previous and Q new, or you could see Q and Q plus. So depending on what you see, all you have to distinguish is which one is next and which one is current. Would a not allowed state be a functional glitch? The not allowed state will not only be a glitch, it will cause the outputs to go back and forth, right? 0, 1, 0, 1, 0, 1. After that, the latch is essentially not functional. I cannot no longer use it for storing or setting or resetting. The only way, there is a way to come out of it though. The only way to come out of the metastable state is to go to one of the stable states, which is reset or set. So if you end up in a metastable state, you can bring that latch back to normal behavior by going to set or reset state. What does that look like on a computer, for example? You never want this to happen in a computer. So what you do is you look for the solution. You see this? You never allow these inputs. So what you actually do is not a set reset latch, but you will want to do something like this, which avoids that altogether. So let me erase this, but I hope you got the idea from this. Let's move on and talk about the characteristic table in a little bit more detail for the set reset latch for the same thing. Now over here I'm going to talk about Q and Q plus, right? So Q and Q plus indicate the same thing. In our case it was what? Q plus we were referring it to as Q, and Q we were referring to as last Q, right? In our characteristic table. So it's the same thing. So what should I write for the table on the left? SR00. What is Q plus? It's a store state, Q, right? Q plus equals Q. That's your store state. It could be a 0, could be a 1, but it is Q, last Q. How about the next one? R is 1, S is 0. Reset state. Q plus equals 0, independent of previous Q, right? Independent of previous output. If you have R as 1 and S as 0, it is going to force the latch to go to reset 0. How about the next one? S is 1, R is 0. Set it. Make Q plus 1. Yes. And then the last one. The last one is 1, 1. But instead of writing 0, I'm going to actually not allow it. I'm going to write that as don't care, because it is a 0, it's a 1, it's going back and forth. Now, using this compact characteristic table, I can expand this into essentially 3 inputs. Why can I do that? Because I'm using Q as one of the inputs. As Q, my previous output could be a 0, could be a 1. So I've essentially made 3 input columns in which one of the columns is my previous Q and the output column is the new Q, Q plus. So what should I write over here? Let me identify the states first, and then we can go from there. Yeah. So what state am I in here? What state am I in here? What state am I in over here? And what state am I in over here? Store, reset, set, not allowed. Beautiful. So for the store state, I said Q plus equals Q. Okay. So in that case, this guy is 0, that means this has to be 0. This guy is 1, so that means this has to be 1. You guys see that? And then how about the next 2 entries? For the reset state, what should I enter for Q plus? For the next 2, 0. Independent of Q is going to be 0. How about the next 2? Set it. How about the next 2? Don't care. You guys see it? So we have expanded the compact table into a 3 input case. Now what we can do is we can take this information and actually put it in a K-map, where your inputs to the K-map are S, R, and Q. It's a 3 input case. I have already filled out the zeros and ones and the X's based on the table that we just derived earlier. And I'm going to use the don't cares only when it helps me. I'm going to use my K-map strategies to figure out what is the simplest form of expression for Q plus. And you will come up with the characteristic equation of the SR latch. Q plus equals S or R complement and Q, where Q over here is your last Q and Q plus over here is your new Q. S and R are the control inputs to the SR latch. You guys see that? So we did this, we translated that into a 3-variable K-map, and from the 3-variable K-map we derived the characteristic equation. Questions about this? All right. Now let's talk about the SR latch operation in terms of a timing diagram. So essentially what we are saying is, if I was given certain timing diagrams for the S and the R inputs, would I be able to sketch the output waveforms for Q and Qn? What I'm going to do is, at the beginning, I'm going to assume that Q and Qn start off at 0 and 1 respectively. So that's an assumption that I have to make because it's an output, right? So I have to assume some starting state. So I'm assuming that Q starts off low and Qn starts off high. And then I will start looking at the timing waveforms here. As which state does the SR latch start in over here? Store. Yes, absolutely. So it's 0 and 0. So it is starting off in the store state. So it will keep Q at 0. It will keep Qn at 1 for that duration of time. Then I have a change in S. The moment I have a change in S from low to high, I go to the set state. The moment I go to the set state, after a little bit of delay, my Q goes to 1, my Qn goes to 0. That is my set state. So I can actually highlight this. This is making that go to 1, that go to 0, but after a little bit of delay. And we can calculate that based on the discussion that we did earlier with propagation delay and 2 times propagation delay, all that. Similarly, after I bring this to 0, I again store it. So this will continue to be there. And after a little bit longer, I'm making R as 1. So when I make R as 1, I'm essentially resetting the latch. So this guy goes to 0, consequently Qn goes to 1. Then again I store it, right? This is all of this is going to be store. Store here, also store here. And you can see during those windows, timing windows highlighted in orange, Q doesn't change, Qn doesn't change. And the last thing that we did over here is to again set it. Q became 1, Qn became 0. And then we stored it. Now, this is going to be quite simple to sketch out as long as we go between set, reset, and store. However, if you have something like this going on, where you change, so this I will sketch in pink, you change from 1, 1 to 0, 0 on both S and R at the same time. You see what happened here. Both Q and Qn went to the metastable state. That is output going back and forth between 0 and 1 continuously. Only happens when S and R goes from 1, 1 to 0, 0. Even if there is a little bit of delay, then you will end up in a store state, set state or reset state, and then you will store, which might be okay. You will not go there. Now let's talk about some timing parameters for SR latches that could also end up in metastability. Why are Q and Qn in sync? Well, there should be some delay. There should be a little bit of delay between Q and Qn. Those are not explicitly written out over here. But you're right. If we were given some numbers, we could actually see them slightly being delayed between each other. Next, we look at propagation delay and we look at the minimum pulse width. Let's talk about minimum pulse width. Yes, you're right, Preston, because it goes through another NOT gate. We are not including that delay in this in that discussion. We are not including that kind of delay in that discussion. We are assuming that that kind of delay is 0. But you're right. There is going to be an asymmetry in Q and Qn as well. Here we are looking at two timing parameters, propagation delay and minimum pulse width. Let's talk about minimum pulse width first. Minimum pulse width is going to be applied for any one of the inputs, say S and R. So this is the duration of time for which I cannot change S or R up and down, right? So for example, over here, the pulse width of S is bigger than the minimum pulse width. This guy is the minimum pulse width here. And the pulse in S is bigger, so that's okay. It's not going to cause any problems. Over here is okay. Over here is okay. But over here, the pulse width is smaller than the minimum pulse duration, which causes metastability in the output. So if S goes to 1 or R goes to 1, it cannot come down immediately. It has to be there for a little bit of time, indicated by the minimum pulse width of the NOR gate. Right? Because it all has to do with that analysis. When we made R as 1 and S as 0, we were able to take advantage of the output from the previous case to store it. But if that output, the input itself is changing, then there is no point. The other timing parameter that we are looking at over here is the propagation delay. So for example, the change in S causing a change in Q is right here. So this is propagation delay from S to Q when Q goes from low to high. P for propagation, low to high, S to Q. And then similarly, there is a propagation delay when Q goes from high to low due to a change in R. And then the minimum pulse width is that window right there. We are obeying it over here. We are satisfying the minimum pulse width here, here, and here, but we failed to satisfy the minimum pulse width at the last pulse, which caused metastability. There is a way to come out of metastability. All you would have to do is go to one of the stable states, which is reset or set. After that, you will come out of metastability and then you can operate the latch the way you want. Okay, some of the SR latch symbols. This symbol where you have two control inputs S and R and two outputs Q and Qn is valid symbol. This symbol also is valid because you have written Q over here and then indicated an active low output by putting a bubble in the front of Q. That is okay as well. But this is not allowed because control inputs are fine, S and R. Q is also fine. However, you have indicated that the output is active low, and on top of that, you have indicated a bubble in the front. So that's not a valid symbol for SR latch. Just a box, and the inside of the box, as we know, could be a two cross-coupled NOR gates, and it would actually be two cross-coupled NAND gates as well. So that's what is next. To SR latch using NAND gates. You could also get exactly the same operation of storing, setting, resetting, and so on with NAND gates. So here what we have is cross-coupled NAND gates with active low inputs. You see, we made S is active low, R as active low, Q is, Q and Qn are the same. I hope you guys look at this and identify that these two guys are the 2 input NAND gates. There has also been another change. In our configuration earlier, we had R as the top input and S as the bottom input. The top input corresponding to Q and the bottom input corresponding to Qn. We also switched that. So the top input now is here S underscore L and R underscore L is now yes, you're right. Because of the not allowed state. So let me just do that. So this is going to be the not allowed state here. This is going to be set, reset, and store. Right? S is active, R is active, both are inactive. So by simply converting the inputs to active low and putting in NAND gates, you can also get the SR latch. Now the obvious question is, how do I know that you put down the things that are, how do I prove this, right? Well, the answer is quite simple. You can actually look at, you would have to do an analysis exactly the same way as we did for NOR with NAND gates. You would start off with set, you would try to store it. You would start off with reset, try to store it. Then you would start off with the not allowed state. You will still get Q and Qn as 1, but then when you try to store it, you will get meta stability. So you can prove it using that. But that's your SR latch using NAND gates. And that's the characteristic table for that. All right, let us stop over here. I guess this is time, and then we can pick it up when we come back.